Control volume approach, which is the one I at least want you guys to learn throughout this course. So the idea of the control volume is you use all Cartesian coordinate system to derive all your x, y momentum and your mass conservation equations. Okay, some side note. So remember at week 1, we mentioned that we will give out a book for the best performing student with Guan's signature on it, sponsored by myself. I pay $110 for it, so it's worth $1. So please try your best if you're really into CFD, so there's more encouragement. So how this works is we can only evaluate up to the coursework, so for the exam it won't matter. So the best performing student in terms of coursework will get a Guan signed CFD book, brand new, and the latest edition with all the updates. And I don't even have this one, so you guys are lucky. So we only started this this year, so yeah, I really want you guys to fight for it because it's really worthwhile of having, and to prove that you are the CFD nerd. Okay, anyways, let's go back to the lecture. So since all CFD are based on the governing equations, we need to develop our fundamental understanding of these terms. So when we discretize our domain, we will solve the partial equation through an iterative process. So that's why you have all the convergence criteria when you start to go to your solver and you see your XY residue and mass residue goes down while you do the iteration. So the more iteration you do, the more accurate your solution will become. And that's for steady state. If you are doing a transient solution, meaning that your result is time dependent, then your iterative process will go every time step, meaning that after the first time step, you will begin from the start, starting from a very high residue, and then you need to iterate for a certain number of iterations to achieve your next time step. But I will talk more about the transient simulation later. So, as I mentioned, the boundary condition also strongly affects the CFD equations. So I give you an example, a 2D parallel plate flow. If you define the flow is totally driven by pressure, then the dP by dx is obviously the force that driven the flow from one side to another. So by then, I would even go to the formulas to derive to you today to further prove what I'm saying now. But beware that in week 5, it is also very important for your CFD assignments to know how to set up the proper boundary conditions. So I think you guys already deal with inlet, outlet, those simple stuff, wall and symmetry. But what is actually CFD putting in terms of numerical as boundary condition? So I want you guys to come to week 5 as well, because chances are many people dismiss week 5 for whatever funny reason. Maybe we mentioned it's not in the exam, so every one of you just don't come. But actually it's quite important, because what we find in the report is you don't know how to describe what's actually happening for your boundary condition, and you lose all the marks for that part. So I strongly recommend you to come as well. So what I'm trying to let you guys know is to come to every lecture. Okay, let's start with the vector equation derivation for the mass conservation. The reason why we take out most of the vector for this course is it requires a lot of vector calculus for you to even understand what's going on. So meaning that you need to understand the dot product, the cross product, and so forth. So the vector operation itself, I believe, is another mathematical course. And as the number of master student increases, you guys are from different backgrounds, so the knowledge also varies. So we don't want to introduce you something that you don't have any background knowledge to begin with. Well, without further ado, so this is a continuous fluid. So I can use my mouse, hopefully, yeah. So this fluid element actually attaches to this surface. But the thing is, it's pretty hard for me to draw that because it's an irregular shape, so you guys can imagine it pretty much. So this is your dV for this control volume element, and this is your normal vector, and this is your velocity vector. And this is your surface area, so we call it ds. So the idea is by invoking the mass conservation law, we know that whatever change for this fluid element in terms of mass equals to the summation of outgoing mass flux minus the incoming. Anyone don't get that? Should be simple enough, right? But how do we put it in terms of formula? So easy, like first thing we know from the left-hand side is dm dt, because that's your rate of change of mass, isn't it? So what about mass flux? Anyone have any idea? Anyone is familiar with vectors? Okay, that's expected. Okay, anyway. Okay, so because even myself, I need to Google what is the physical meaning of, the dot product. So it's actually a projection of one vector on the other vector. So why we need to, in terms of mass flux, why do we need to do this operation to get all the mass flux? And why is it minus, you may ask? Because the rate of change of mass, when it increases, that means you have more incoming mass flux. But if you look at this figure, the outgoing mass flux is pointing to the positive direction, so incoming is minus. So that's answer your question. Okay, and the other question is why rho v dot n? It's because rho v is your mass flux. Everyone should know that. Okay, so when we do v dot normal, that means we are finding the vector projecting on another vector. And we want to consider the mass flux of this surface going out normal to the surface. So that's why we need to do a dot product. Okay? But I will put on more legacy contents in an extra folder in case you guys want to learn more about vectors. But I need to further re-emphasize myself. This is out of the scope of this course, so don't dream about you will score extra mark by reading the legacy contents, okay? Okay, so once we derive this formula, this is dm dt, by the way, I'm being lazy. So mass equals to density times volume. So integral V against volume will give you V. And then that's rho times V, that is M. So this dm dt, but I skip one step here. So another theory you need to introduce before we even can derive the general form of the continuity or mass conservation equation. They are the same. Continuity equals mass conservation, by the way. So we need to introduce this Gauss divergence theorem. Why so? Because you see these integrals are in different, with respect to different things. One being the volume, one being the surface. So if we want to combine both sides together, we need to use the Gauss divergence theorem to change the right-hand side into divergence of rho v. I will explain what is divergence later. Okay, so once we do so, we put this into this equation, put the minus to the left-hand side, so it becomes a plus, everything plus on the left-hand side. And then integral by v equals to 0, so we can take out the integral, and then hence we come to this form, which is the general form of the conservation laws. And this will agree to what we are going to derive in the control volume method as well. So every one of you may know, like, you are most likely solving the incompressible form of governing equation. So Of course, there will be some simplification here. But since we are not talking about vectors this year, I may need to talk from the Cartesian coordinate system perspective. So what divergence essentially means is, if you put it this way, is you partial differentiate everything with respect to all the spaces. So you have a 3D system, you differentiate your rho v by partial x, partial y, partial z. So here's how you come to this form. And then the first part is just a local derivative against time, so we leave this term. So if we directly transform the vector form to this part, you will come to this equation. So now let's go to the important part, which is the conservation laws. So I would like to derive it in front of you. Maybe that will enhance your understanding a bit. Sorry. I'm still getting used to this lecture hall. Sorry. Bear with me. Does the computer block your view? Like for the bottom part? Anyone? Yeah, okay. Okay, then let's go. Okay, no complaints afterwards, please. Okay, so if we begin with infinitely small fluid element, so I normally just want to draw a square. So we have the axis, and I normally like to put this as the x direction, and on top is your z direction, and at your lateral position is your y direction. Okay? So assuming this is infinitely small, this becomes your dx, the distance between. Oh, okay. That can solve your problem. Okay, and then that becomes your dy, and correspondingly, this becomes your dz. Okay, so we all know that the mass flux at this phase is rho u, and then times the area of this phase. I will just call it ax by now, but if you come to think of it, what is ax? It is actually dy times dz. So this actually equals rho u dy times dz, right? Okay, here comes the hard part. So we want to know what is the mass flux of this phase. But little do you know, because you travel around for delta x of the distance, the mass flux actually partially changes because behind your fluid element will push your fluid forward. So you have a partial change to dx. So how we normally derive this, we use the Taylor series expansion. So the Taylor series expansion essentially is, if you start with a function, x plus dx, is actually equals to the function of its original position plus delta x, 1 factorial, the derivative, the first derivative times dx divided by 1 factorial. That's how I remember it. And delta x squared, 2 factorial, second derivative, and then you go, just keep on going, like the x cubed over third factorial times the third derivative. But we only need the take to until the first order. And then we consider the other terms as higher order terms. And then we ignore everything. So we use a first order approximation. Okay, So now what is the first derivative? Oh, no. Okay, if you put your function now equals to rho u, what is okay, here's the question. So it's easy. So your rho u at x plus dx equals to, first thing first, fx. Fx is rho u, and then plus dx divided by 1 vectorial, and then d rho u by dx, right? Everyone got that? Okay, and then plus higher order terms. Okay, so if you look at the lecture notes on your right-hand side, that's how you derive that flux over there. And this same concept you will be using for the momentum equation as well. But since the momentum equation has more terms, I won't repeat myself on this. So you just remember how we do it mathematically here. Okay, so so we move to the next step. And again, once we define all these terms, this is actually your rho u plus the rho u dx pi dx times the area, which is dy dz again. Oops. Oh, maybe I'll go back. Because the area is the same for the fluid element, it's also dy dz on the right-hand side as well. So that's how you do it. So the next step is to take the outgoing flux minus the incoming flux, because your axis always go to the right-hand side. So as we know that dm by dt equals to so that's simple. So in rho u dy dz minus out rho u plus so this two term is equal, so we can take it off. Oh, sorry about that. Okay, so you leave behind with minus d rho u dx, dy, and dz. And I can already know what will go for the y and z direction, which is by similarity, the rho v dx, and then you also have dx, dy, dz. This equals to dv, which is your volume. So I'll just put dv. And if we break down the mass term here, so you will have your rho times volume, rho dv, okay, so since both sides has dv, we can take off everything as well. So what we come back to, we put everything on the right-hand side to the left, plus So it's exactly the same as the vector form of the derivation. Surprise. Well, yeah. Okay, so that's pretty much it. So any question up to this point? Okay. I know some of you guys may thought, this is so easy, why spending all the time do this, making it so clear, but believe it or not, I receive a lot of complaints. So this time I make sure myself is very clear. So now we want to introduce a very important concept to you guys, which is the substantial derivative. This is important because if we want to invoke the incompressible flow, we can reduce the continuity equation significantly. So the concept is here. So we start with the continuity equation. So since this is a product law for the derivative, so you can expand it into two terms. It's like the multiplication law of the differentiation. And after you expand this form, you can, for the first four terms, you can put it as big D rho over big T. That's your substantial derivative. So what's the difference between a partial derivative and a substantial derivative? So substantial derivative here, we are following the particle and then or the fluid element, and then we move alongside while we are doing the differentiation. But the second one, we fix our perspective on the same point, and then we consider everything incoming and outgoing. So for the substantial derivative, we normally use it for particle tracking in CFD. So say if I want to model the sprinkler and I want to monitor the droplet going down, trace its position, we use the big D. If we just want to solve the whole domain, just the CFD equation, we normally just solve the partial equations. Okay? So another important concept is when the flow is incompressible, what's happened? That means if your flow cannot be compressed, first of all, your density always remains constant. So your substantial derivative term goes away because it's always a constant. So you differentiate it, it will give you 0. Simple. And then you will leave with du dx, dv dy, and dw dz. And that's your divergence of the fluid. So the divergence of the fluid element, for example, the rate of change of all the mass flux is equals to 0 when your flow is incompressible. I repeat, when your flow is incompressible, your density is constant, and then your divergence of your fluid, meaning du by dx, dv by dy, and dw by dz partial, is equal to 0. Okay. I always repeat myself because I know what question will be coming out in the tutorial set problem. So, yeah. Okay, so this substantial derivative is also important while we are deriving the momentum equation. So, as I mentioned, you can apply to anything. So, let's say, for example, we have any property equals to phi. So d phi by dt, big D, equals to your local time-dependent term plus your free spatial terms. So u d phi by dx, v d phi by dy, and w d phi by dz. Okay, but what about the rate of change per unit volume? Then we just add a rho in it. So rho times everything becomes per unit volume. So you add a rho in it, the equation remains the same, but you just have rho on both sides. But that's very useful because while we are deriving the momentum equation say if we put phi equals to u, then we can use it on the left-hand side, because while we're doing the rate of change of momentum is big du by dt. So we need to convert that by some equations. So again, if the flow is incompressible, this part automatically goes to 0. And why so? Because density, when density is a constant, you can take it out from the bracket as a common variable. So you will leave with du by dx plus dv by dy plus dw by dz. And when incompressible, it is 0. So this part is 0. And of course, your d rho by dt is also 0, because when it's incompressible, density doesn't change. So here comes the momentum equation, which is essentially Newton's second law, F equals ma. But it's not actually as simple as F equals ma, because the computer cannot solve that. So what we need to do now is to further break down the mass times acceleration part, and also identify all the acting body force or the surface force on the fluid element itself. So it's very similar to the concept for continuity equation. The only difference is when we deal with continuity, we do it for all the 3 dimensions. But when we solve the momentum equation, we do one by one. So for example, we give you the x direction first. So these forces acting on the body is actually just for the x direction. So we have our normal body forces, stress. So that's your normal stress. This term means normal stress. And again, using the Taylor series expansion, you get this term over here. And then you also have 4 more surfaces where your fluid element will shear against each other. So imagine if my top fluid is going much faster than the bottom fluid. It will create a shear force, shearing the bottom part to go faster as well, right? So that's where I'm coming from. So again, using the Taylor series expansion, you know the changes in dy as well. So that's how you come with the top part. So once you identify all the forces, then it's the painful part, which is a lot of algebra derivation. So I won't do it for you guys. You guys need to do it as an assignment. So, but the concept here is simple. So we first start with F equals ma, and your acceleration obviously in the x direction equals to du by dt. And then you need to explain this by a substantial derivative equation. And then I already mentioned to you, there are the body forces and the surface stress forces. And did I hear any question? Okay, no, okay. So the body force can be due to any external or acting forces, but normally you only deal with the pressure difference. But other force mainly includes gravity, centrifugal, coriolysis, and electromagnetic. I don't know. This Guan put this too, but we never use it anyway, so just forget about it. Yeah, gravity is a thing. So in the CFD equation, sometimes you need to switch on the gravity. So if you derive your domain where your y direction is the vertical position, your gravity is always minus 9.81 in your y direction. Okay, but for more information, ask those guys over there. They should be able to answer. Okay, so you have your normal stresses and your tangential stresses or your tensile stresses. And just for the x direction itself, after all the elimination of the terms, you will leave with this equation over here. And then we need to sort of find a way to approximate what is the tangential stresses and the normal stresses. So it is suggested that the rate of linear deformation of the control volume can be expressed in terms of velocity gradient and the pressure. So for your normal stress, this is where your pressure terms comes in. So, and then for your tangential stress, we apply the Newton laws of viscosity. This law can be only applied when the fluid is Newtonian. Okay? So, yeah, so you notice that this is a linear relationship against your the partial difference of your velocities. So that's, yeah. It just depends on the fluid. So in your, yeah, in your, if you are, I don't think you're solving blood in this course. So, well, yeah, we will be only doing Newtonian. So that's why I'm trying to avoid, like, you know, putting in the Newtonian equations as well. But you're right, like, the reason why if we are doing blood or we are doing some bubbly flows or whatever, then the particle will affect the viscosity, it will affect the properties of the fluid, then you can't formulate a linear relationship because your mu doesn't stay constant. So it's actually, yeah, there's some more derivation for mu, for even density as well. So it will be too advanced for this course itself. So, okay, so let's go back to here. 36 minutes. I'll talk 10 more minutes, then we'll have a break, short break. Okay, so this term here is derived by Stokes' hypothesis. I can't remember it. Okay, so lambda equals to minus 2 over 3 mu. But when the flow is incompressible, as I mentioned, this goes to 0 anyway. So if you don't want to even write this term, you can just ignore it. This is how I do it when I derive this. And then you put everything together. This is rotational stress, I believe, because I know it when we still have the vector form of the derivation. And we introduce another term here, kinematic viscosity, which is dynamic viscosity divided by the density. So if I want to put it easier, it's just the viscosity of the fluid element per volume, again. So it's just another way of writing. I normally like to use everything mu. So when I derive this equation, I will write mu over rho. But it's up to you. If you want to put it simple, then you can just put this v. But it always confuses me because it looks so similar with the vertical velocity. Like, I mean, when you write on the paper. Okay, so after putting everything together and with a lot of algebra derivation, which you guys are going to do and submit to me next week, Friday, and you will arrive to this form. Okay, so don't be overwhelmed by all these terms here. So in all governing equation, we always have 1, 2, 3, 4 terms. We normally ignore this part because we just write, because this is the conservative form. This you can ignore about it because we are not dealing with particles. So we have the local acceleration, the advection. This is actually the source term, but here there's no other source term other than the pressure gradient itself. So I put pressure gradient here. So here's your diffusion term. What do they actually mean? For the local acceleration, if your flow is time dependent, meaning if your velocity changes against time, then you will have some value for the local acceleration. So all your time-dependent variable will be fit in this du by dt or d whatever by dt term. That makes sense. So that even accounts for unsteady flows, where in case you have an earthquake-driven flow, then your feedback will be something like that. That's also accounted in the time-dependent term. Okay? And the advection term and the convection term, you notice that you always have the velocity component in front of these terms. So imagine you have a very large u velocity, this will dominate the force of your flow. So that's accounted in the advection or the convection term. They are the same. So that's why I put it this way. Or you can put it as the inertial force of the fluid flow, which carries from the beginning of the channel to the end of the channel, if your flow is advection dominant. But if you have a very large viscosity of the fluid and your fluid is very diffusive, then your diffusion term will be more dominated. So whenever your Reynolds number is high, then because Reynolds number equals to rho u something over mu, right? That means your advection term will be dominated. But whenever it's low, then your flow is more diffusive. So low Reynolds number, I give you an example like air. So air, you always, it's when I say I breathe and the air will always disperse. Why? Because the diffusion terms dominates. So diffusion actually physically means that the higher concentration of that quantity will diffuse to a lower concentration. It's like osmosis in biology and something. Yeah, to put it simple. And this is all accounted in your second derivative terms. So whenever you have second derivative, that means diffusion. And this will be further elaborated in around week 9 or week 10 in the first order approximation of the second derivative or the second order. But don't need to worry about it now because it's not too important now. And for this particular case where there's no body force and the fluid is incompressible with constant fluid properties, we only have the pressure gradient driven the flow. Okay, I see some yawning. Maybe we'll have a break for 5 minutes. Okay, feel free to come and ask me any questions.
Zach. I was it's like a yeah. Harrison's actually different. Yeah, because he moved as well. Oh, did he? Yeah. Because I wanted to, like, I let him know, yeah, it's like, oh, what are you doing here? Yeah, because, yeah, there's a bunch of college. I guess there's yes. How you find it? The lab. You did everything. Yeah, so it's like yes, excellent. Yeah, I think we lost this thing before. Yeah, I mean, so I realized the next lecture, that's just like his lecture style off at like that point in time. This is just like talking about like, oh, I remember this, I remember this style, like, and just like, so I'm gonna pull my head with this yeah. I don't know, I've looked at a couple of like Yes, yes, yes. You're just trying to do it. Yeah, no, because I expected that to happen. Yeah, like that's like yeah, I thought and probably get to like yeah, so it was jumped. The last one. Yeah, and I did like, I was doing so I did like, I meant to do like 2 5-minute courses to go.
And then see what
I think it's yeah, this one, like,
Okay, let's come back. Attention, guys. Oh, I don't. Sorry, get my microphone back. So let's move on. Starting from all the terms here for the momentum equation. So where did I stop? Around diffusion, right? So source term, we have, for this particular case, just the pressure gradient. So I will further explain how the pressure gradient can drive a force from a working example later. So this source term, you cannot generate any velocity or dissipate and make the velocity disappear unless you have a source term. So if you have a plus source term, you're introducing a source. If you have a minus, you're making something disappear. So for all the parts, it is always conservative, but you can only generate some quantities or make it disappear through the source term. So I'll give you an example. If I have a heat source, then my source term will become something like omega T, and it will be, if it's a positive source term, then it will create heat for if I'm solving temperature for, say, the energy equation, which I will talk about next week. That's a good, easier example to understand. Okay, so if we consider this working example where a flow, a uniform velocity, is injecting into a parallel plate problem, and then you know that if the flow is laminar, you will get a parabolic profile at your outlet. And of course, the flow is also steady, meaning it's incompressible with constant fluid properties. So we can start with the momentum equation and derive this from a mathematical perspective. I'll show you how. Okay, so I know in the slides I automatically tell you du by dx is 0, but where do we arrive to this? So if you remember, for the continuity equation of your mass conservation, oops. Yeah, I can do this. Sorry, I skipped a lot of steps. But I think you can find this equation in one of the slides anyway, so it's okay. So that's the general form of the continuity equation after you expand it using chain rule. So if the flow is incompressible, meaning d rho dt or d rho dx or etc. equals to 0 because rho is a constant. So this also goes to 0. That's your, and the divergence of the fluid, meaning du dx plus dv dy plus dw dz equals to 0. Oh, no, sorry about that. let's not go to this. That's what we want to derive. We want to go to this equation. So once we know this goes to 0, we are only left with rho times du dx plus dv dy plus dw dz equals to 0. So that's how we derive where the divergence of the fluid is equals to 0. So if you look at the parallel plate problem itself, the velocity is only with respect to the x direction. Okay, if we reduce this to 2D, we get this as our incompressible form of the continuity equation, right? So since we have, in this parallel plate problem, every velocity is only at the x direction, we have no vertical velocity. That means v equals to 0. So this goes to 0. So that's how you arrive to here. So using the continuity equation in compressible form, we can come to this. Okay, now we need to look at the momentum equation in the x direction itself. So again, if I want to start from the right-hand side, I just want to do a 2D case. I can ignore all the du by dz terms. So I will leave with sorry, I can't afford to speak because I need to be careful when I derive this. Okay, so what we learn from this expression here is all the du by dx is 0, right? So we can automatically put this at 0. And then another thing we know is because v also equals to 0, so this term also goes to 0, right? And we assume this case is a steady case. Meaning your properties change is 0 because there's no change, no time-dependent change of the fluid properties. So this will go to 0. All right. Okay, so now what we left is, okay, sorry, there's one more thing. This also goes to 0 because the first derivative is 0, the second derivative is also 0. Okay, so we are left with mu over rho d squared by u by dy squared equals to 1 over rho dp dx. So this will give you, move the left-hand side to the right-hand side. And u is a function of y. So this is your function. So based on just the continuity equation and the momentum equation itself, we can derive this second derivative profile, meaning your flow is just purely driven by the pressure gradient with respect to your x direction. And the second step is to find uy. And how do we do so? We need to do some secondary school mathematics, which is integration. Okay, this I don't need to go here. You can just look at the slides. Okay, so if we go back to the slides, we know that the second derivative equals to 1 over mu times the pressure gradient. Integrated once, we have a constant C1 appearing. That's the integration law. We integrate again, then we have C2 kicking in. So I won't further elaborate this. So the next step is to define the boundary condition to find what C1 and C2 actually is. So how can we do that? If we look at the flow profile, you notice that at this very tangential point, where at the middle of the channel flow, there is no change of the pressure gradient. So if we define the middle point as, I forgot what I defined, sorry. Okay, u equals 0. Okay, so first of all, the easy thing is at the wall, there's always no velocity. So if your point is h divided by 2, which is halfway up of the channel, if you take the middle as the origin point, so half of the channel is where you hit the wall. Then u equals 0 as y equals to h divided by 2, or u equals 0 at y equals minus h divided by 2. That's your no-slip wall boundary condition. And as I mentioned, there's only one point where your velocity gradient doesn't change, which is at the middle of your outlet. So when your y is at 0, which is the origin, then your partial u by partial y is equals to 0. So you apply these two boundary conditions into this equation. You have two boundary conditions, two unknowns. You can obtain C1 and C2. Okay, so I think that's pretty much it in terms of equation. Okay, so now it's just some minor discussion about this fluid flow problem. So it is actually discovered a long time ago in 1988, where all laminar flows follow this behavior by Nakayama at the year where I born, 1988. So yeah, so that's why I want to bring that up. And then the flow is parabolic, and it will be always true for laminar flows in parallel plate channels. And if the flow is turbulent, however, it will behave very differently. As Guan already mentioned to you guys, you won't develop to this perfect parabola profile. You will remain something similar as your inlet flow. The reason being is we can explain actually through the governing equations as well. So imagine if you have a super large Reynolds number, then your diffusion term doesn't really matter. It becomes a very small number. And then if you have a very large advection in comparison to your diffusion, then whatever velocity you put in, it will equivalent to the velocity you go out. So that's why your outlet profile retains its shape when your flow is turbulent. If you don't understand, you can come to ask me. I know it's very hard to explain in words. But again, next week I will generate a CFD problem for you. Like I will compare a water flow against an air flow so you get more understanding of what's actually happening. Okay, is it finished? Okay, whatever it is. Okay, that's finished. I just want to give you some hint for the group assignment since we have time. Why not? So if you are in odd number groups, you will be working on the arm body flow. So if you are in even number groups, you will be working on the heat exchanger problem. Attention. So both of which are at similar difficulty. One being requiring more of the meshing, which is the arm body, and the other requires more understanding of the heat transfer or the energy equation, that's being the heat exchanger. And some of you already asked what happens. Do I need to know about, when does the diffusion and the convection dominates when I'm dealing with the heat exchanger? That's actually a good question. So my answer is yes, definitely. Like, if you can answer that in your report, you will score a higher mark. Okay, so anyway, both of which requires a user-defined function to calculate, for example, the arm body. You need to calculate the lift and drag, which is the main point. And then from there, you optimize your lift and drag by changing your flap angle and whatever. I will show you in I just did it for fun yesterday. Yeah, so there's your whole group project. If I can do it in one day, you guys can do it within 5 weeks. No, I'm just joking. Yeah, so you can either tackle this problem by 3D or 2D. And some tutors mentioned to me 2D is actually not so bad because you can refine the mesh even further. Because if you do 3D, you need to put more mesh on the depth as well. And your limit is always 500,000, by the way. So you can't go beyond that, unfortunately. So, but we test this case already. No matter 3D or 2D, you can get a reasonably well result. But what I want to show you in this result part is what is your objective for this problem itself. So if you follow the instruction of the question sheet, then you will notice you can use the function calculator, and then you can evaluate the force acting on this arm body. So, and then you need to define what direction you're looking at. If you're looking at the drag, then you should always look at the horizontal position, which is X. So that's your current drag. But obviously, if you want to design a car, you want fewer drags, but you want fewer lifts as well. You don't want a car to lift up, so you need to get a well-designed to get a good balance of these forces. We also give you an equation of group assignments. Okay, arm body. Okay, so in case you don't know how to evaluate the lift and drag, there's your equation. So just put in, I just show you the force here, fit it into this equation, calculate the coefficient of drag and lift. Okay. Okay, so the idea here is to introduce a flap. Oh, sorry, it's actually this way around. Like I know it's a funny shaped car, but this is a very traditional case. So you can introduce a flap here to improve the drag, but it will make your okay, fluent with flap, with no flap. Okay. So here I put a flap here, a small flap. That's what you need to do. So that's very normal for a typical car. But it will totally affect the flow dynamics of this vehicle itself. So after I put the flap, you can see there is a big change. Force, car body, X direction again. You can see the drag significantly increases. So the flap does not necessarily improve the design. But what it will improve is it will make your car to be stick on the ground. Yeah, thanks. Okay, so the other project. I created the heat exchanger maybe 1 year ago, and at that time it wasn't perfected, but I believe now it is well designed enough so that you can start with something. We will start with a mediocre design and then improve from there. So our previous mistake is we already give you a perfect design, so it is very difficult to improve from the design we gave you. So what we change here is we increase the size of this heat exchange box. So the idea here is simple. You have a cold fluid region. For example, we put cold water in and then flow across. And then we inject some air in, like an air conditioning unit. Our objective is to lower the temperature of the air. So at the moment, you can see, again, I go to the calculator. The outlet 2 is actually here. I know because I do this. At the moment, it's around 8 to 9 degrees. Believe it or not, for an air conditioning unit, it's not too perfect. I believe you can reduce this even further. So I give you a hint here. The concept is always the contact surface area. So you need to increase the amount of contact surface area. And obviously, you can change the refrigerant as well, but that comes later. So I believe that's all I want to deliver for this week. So thank you for coming, guys. If you got any questions? You can change the trajectory.
I like this morning. I just did like the cat of the fight, and I'm putting that into answers, and then like putting a primitive box over the top of it. Do you think that's probably the best way to do the?
I think there's a lot of ways. So you only need to do it for you, but more important is I want you to explain how.
It's just like greater surface area, and then it'll have like transparent.
Not only that, like if you can talk something like diffusion, better diffusion.
Yeah. Okay. Yeah. All right. Noted. And are we going into any more like meshing detail in these classes, like how to use all of the different functions of meshing in ANSYS, or not really?
Not in these classes.
Okay.
Yeah.
In the
Because
tutorials.
we have to do
all the other stuff. Yeah. That's okay.
It's an exam. You guys would like me to do that.
Yeah.
But in terms of meshing, you can always go to our experienced tutor. They can give you a lot of advice.
Yeah.
Yeah.
Yeah, I'm just having issues at the moment. I'm doing it for my thesis as well, but like I've got
I remember.
the hard stent, and I just
How
don't
did
know
it
how to.
went?
It's not very well. I'm still trying to like change it, but
I'll
I
have
think.
a check on.
Are you going to be in the tutorial?
Yeah.
Okay, yeah. Because if I can't like fix it today, I'm just going to have to go with the crappy mesh and just like run it because I need to get 30 of them done in the next week or two. So I'll just stick with
I
that.
think objectives is also the most important.
Yeah, it's just like I need to get them done. It's like if I can't get it perfect, I'm just gonna like. Anyway, yeah, I'll be in
All
the
the
tutorial.
best.
Thank you.
Hi, just wanted to check if I can switch to another topic.
Oh, topic.
Yeah, because I'm doing this course for my thesis and I'm doing parallel space field. So because I'm assigned to the seminar, so I just want to practice more in the helpful.
Is that possible, King? Do you want to do it? It's up to him.
We understand that many students want to bring their own thesis topic or their work-related topic. I personally, I mean, if I'm thinking of what's your benefits, I would probably say try to
thank you.
the reason for that.
Bring my topic. My group is assigned.
Yeah.
And I mostly I can to practice those
You mean you want to, changing from heat exchanger to the airfoil?
I'll let him deal with the other groups. So if he can find a member that is willing to swap.
It's
If you have a friend that is willing to swap and you convenient us, make it easy for us, then we will put it as a proposal.
Yeah, okay.
But you need to do the work. You need to ask everyone,
So
and then you make sure that guy has no problem for it, and then you send an email to Chang, and then say, this student is willing to swap with me, and he has agreed, and you need to put him in the email as well, and then he needs to say agree, and then we can do that. Because it has to be fair. And have to be more procedures. If not, then every student will just come to me and switch, Do things properly. Then if we approve everything, then it's okay.
Was there any assigned to L that
So you find anyone?
Odd group.
So which group are you?
12.
You can either go to 11 or
11 or
13.
13. Anyone.
Yeah, but if you can't find one, then if you stick with your own problem, it's not that much deviated from the other one anyway. Seriously.
I would usually the option to practice something more aerodynamic to what research.
I know he wants to do perfect because of this book.
If you can find anyone who's going to swap the groups,
It's not important. They look at the fluid entity, they know when there's no partial, the partial part, then means that whatever comes in those are self-explanatory. Or if the du, dx, dv, dy, dw adds to 0, means the total sum of the thing is
if it's not a structure, which is a triangle, how handle if it's not
we learn nothing about formula before, so that's forget about it.
I'm just
I know it's the least square method. They take all the points and then they approximate the bases.
so they like changing from the triangle into a square and then upon mapping it back.
No, totally wrong concept.
need to learn CFD. So I'm thinking about that. So I know one's code, if it's fully structured, it can do that work.
One is in the experience. You need to find something normal, orthogonal experience. They have multiple ways of solving that. I believe the way ANSYS solves it is way more advanced than you understand. It's not just this script. They must have an optimization for that, not the code run like slow. Okay, let's go. I'm not in perfect condition, by the way.